Hello, and welcome to this presentation on horticulture lighting from Osram Opto Semiconductors. LEDs are dominating the light source market due to their high efficiency, long lifetime, and optical flexibility. Especially for the horticulture market, LEDs can provide additional benefits, such as flexibility of the spectrum, which influences the plant's biomass, shape, color, and how the plant tastes and smells. Multiple market analysts and industry leaders predict a fast-growing market for the horticulture LED industry, with a CAGR of 26% within the next 4 years. There are several reasons for the significant market size development. The first is urbanization and demographic changes. By 2050, there will be an estimated 10 billion people on the planet, and a majority will live in big cities, which will influence our food supply chain dramatically. The second is the legalization of cannabis and its acceptance for medical treatment. This will shape the production of cannabis towards a highly efficient industry. The number one light source for plants used to be high-pressure sodium. LEDs, however, are more energy efficient, generate less heat, and can show longer lifetimes. With these technology changes, producers now have the choice of different spectra based on crop type. This will consequentially lead to a further transition from high-pressure sodium to LED. It is well known that factors such as temperature, humidity, root zone temperature, wind, water, nutrients, and oxygen and carbon dioxide levels play an important role in regulating the growth of plants. But at a basic level, plants need three components to grow: light, water, and carbon dioxide. In addition to these factors, light plays a major role in the growth cycle of a plant through photosynthesis. Various properties of the light interact to control the growth and development of plants. The right spectrum, the efficiency of the light source, the level of the light intensity, the lifetime of the LEDs, and the investment plus electricity costs are the most crucial parameters for a successful horticulture lighting system. Let's first start with the light spectrum. Every light source provides a certain spectrum. The sun, as a natural light source for photosynthesis in plants, provides a broad spectrum of different wavelengths, ranging from ultraviolet, visible, and infrared light. Plants, however, only absorb photons in a specific wavelength range. This range is called photosynthetically active radiation, or PAR, and ranges from 400 to 700 nanometers. The horticulture industry measures the performance of a luminaire in photosynthetic photon flux, or ppf, which is the amount of emitted photons per second. Photosynthetic photon flux is expressed in micromoles per second. This is analogous to the intensity of a light source. The efficiency of a light source is measured in photosynthetic photon efficacy, or PPE, and is defined as ppf per watt, which can also be written as micromole per joule. The measure of the amount of photons, or light that reaches the plant canopy, is photosynthetic photon flux density, ppfd for short, which is defined in micromole per second per meter square. This is analogous to illuminance. Chlorophylls, or the green pigments in plants, are mostly responsible for photosynthesis in the PAR area, which have specific absorption curves in the blue range of 450 nanometers and the red range of 660 nanometers. As a result, the most efficient way to grow plants is a mixture of these two wavelengths. Studies and experiments prove this theory and show that a red-blue spectrum clearly results in an increased percentage of biomass than that of a white light source. Broad-spectrum white light contains energy in the green wavelength band, which, in most cases, cannot be absorbed by the plants. This is the reason why many greenhouses appear to illuminate plants in a pink or purple color of light, which is a mixture of 660 nanometer red and 450 nanometer blue wavelengths. After choosing the right spectrum, it is important to have an efficient system. The total costs of a horticulture lighting luminaire are investment costs, which are fixed, and electricity costs, which are variable. As horticulture luminaires reach 1,000 watts or more, a lot of energy is required in a greenhouse, which supports the need for an efficient light source. Generally speaking, the investment costs of high-pressure sodium lamps are 2 to 4 times lower than that of LED systems, but the return on investment of an LED-based luminaire can be as low as 1 to 2 years due to the lower energy consumption. it is worth noting that between LED systems, there can be significant energy differences, and because of that, it is very important to choose the LEDs used within the luminaire wisely. An important parameter in this regard is called wall plug efficiency, which defines the ratio between optical power and electrical power. Or in other words, what percentage of power is converted into light. The most efficient high-pressure sodium system available can reach a wall plug efficiency upwards of 50%. The most efficient LED system, using a combination of hyper-red 660nm LEDs and deep blue 450nm LEDs, can achieve values above 80%. These two wavelengths are perfect for horticulture applications, which are needed for plant growth. White LEDs are still more efficient than high-pressure sodium systems, but with a wall plug efficiency of 66%, this option is clearly behind a direct-emitting red and blue combination. So why do white LEDs show a significant efficiency gap versus direct-emitting LEDs? Let's look at a white LED in more detail, specifically the light output losses. A white LED uses a blue-emitting chip, which generates high-energy photons. In order to convert this blue light into a broad spectrum, the blue photons pass through a yellowish phosphor conversion layer. During the conversion from blue to a broad spectrum white light, a portion of the energy is converted into heat. This loss of energy is known as stoke shift, and is one of the main reasons why white LEDs have a lower efficiency as compared to direct-emitting red and blue solutions. Red and blue wavelengths are the engine for plant growth, but for some applications and specific plant species, green light is also required. In these cases, a white LED can be added to the spectrum. The use of white LEDs offer numerous advantages, but do come at a cost, which is efficiency. To still achieve a high system efficiency, it is necessary to fine-tune the conversion of the white LED. This is why Osram Opto Semiconductors engineered a new white LED for horticulture applications. Imagine a white LED, which is used for office lighting, street lighting, or even in your living room. These LEDs incorporate green, yellow, and red converters to guarantee a nice light appearance. For horticulture applications, however, a direct-emitting 660nm hyper-red LED is the most efficient option to realize photosynthesis. This leads us to the idea to remove the red phosphor from the white LED. This new concept of a greenish-white LED was realized by Osram OS with the Oslan Square Horti White. Not only is the Horti White LED more efficient than a standard white LED, it offers a real advantage when using a red and white system. Here's an example to visualize the advantage of the new Horti White LED. Imagine a red-white spectrum with 15 660nm hyper-red LEDs and 39 4000 Kelvin Series 70 white LEDs. This will result in a spectrum with 13% blue, 33% green, and 52% red share of the spectrum. At the binning condition, the typical performance of the system will have a certain efficiency measured in micromole per joule. By removing the standard white LED and replacing it with the Horti White LED, it is important to note that the share of high-efficient hyper-red LEDs will increase. With this change, it is possible to realize a spectrum which has the same percentages in red, green, and blue wavelength bands, but now with up to 10% higher system efficiency. This is due to the fact that hyper-red LEDs have a significant higher efficacy than that of white LEDs. To sum it up, the advantage of a Horti White LED is not the LED itself, but the possibility to increase the red share in a red-white system. Luminaires for horticulture applications also need to provide a certain amount of photons to guarantee efficient plant growth. The light intensity required for different plant types varies. Typical values used in the industry for a few crops are shown here. Tomatoes require a photosynthetic photon flux density, or PPFD, between 300 and 500, lettuce between 150 and 300, and cannabis between 300 and 1100 micromole per second per meter squared. A higher photon intensity generally leads to more plant growth by means of photosynthesis, but this process is limited and depends on the levels of carbon dioxide the plants receive and process. For each crop type, a different logarithmic shaped curve applies. This chart only serves as an example. For a grower, it is necessary to find the right intensity of an LED fixture for each specific crop type being grown in a greenhouse, while considering CO2 concentrations. Lifetime and reliability are critical and important factors to consider before investing in horticulture lighting systems. Harsh conditions in greenhouses, such as high humidity, high temperatures, and high sulfur concentration in the air, require LEDs to meet the highest quality standards. High-power LEDs from Osram OS fulfill the highest robustness standards. The Oslan Square Hyper-Red LED, which is the most used 660nm LED on the market, has over 17,000 hours of test data behind it. From this, a Q90 of over 100,000 hours can be projected. Even at a temperature of 105°C, you cannot see any significant PPF degradation. It is always important not to look at only the LMAD test reports, but at hydrogen sulfide and humidity tests. Test results of Oslan Square Hyper-Red show extremely high stability against humidity. Sulfur from fertilizer can have an adverse effect on sapphire chip-based LEDs due to their need for silver reflectors. The technology used in Osram's white, blue, and red high-power LEDs do not require such features, leading to superior corrosion resistance. In addition, flip-chip sapphire-based LEDs have small thermal pads, which lead to hotspots across the thermal pad, resulting in lifetime issues and premature failures. After testing, measurements of a flip-chip LED show a significant drop in light output after only 7,000 hours at 105°C. That means a greenhouse owner faces significantly less light output after just 1 to 2 years. This drop in light output results in less photosynthesis, less biomass, and consequently, a lower return on investment. This all leads directly to the last crucial parameter, total costs. If we compare system cost at the same efficiency level, there's a simple rule of thumb, which is the more white you use in the system, the higher the investment costs. In this chart, the bar on the far left is 100% 660nm hyper-red, and on the right side, 100% white LEDs are used. This considers industry-leading efficacies for both LEDs. There is an exponential relationship between the system costs and the percentage share of white light. A 100% white light solution results in a greater than 700% higher cost than 100% red light compared to the same efficacy level. For the same efficacy level, shown here are 3 different spectral approaches and their relative investment costs. If the application allows for it, it is always recommended to use a 660nm hyper-red plus a 450nm blue dual peak spectrum. This keeps the part count and cost down. If white is required in the spectrum, a lower percentage of white is often the preferred option to maintain high efficacy. We will discuss a modified spectrum called Horti-White later, but this can help you maintain higher efficacy levels. The solution with the highest investment costs at the same efficiency level is a red-white solution using a majority of white LEDs. Osram Opto Semiconductors focuses on LEDs for all horticulture applications, such as top lighting, interlighting, vertical farming, and consumer lighting. The broad portfolio offers mid-power and high-power LEDs in all the relevant wavelengths, with industry-leading efficiency and highest quality standards. As the industry-leading standard, the Oslan Square Hyper-Red LED offers the highest efficacy in the market. Direct emitting at 660nm, the Oslan Square Hyper-Red achieves 4.34 micromole per joule at 350 milliamps. The LED reaches an output of 5.71 micromole per second at binning conditions and 11.16 micromole per second at the max driving current. Even at the maximum driving conditions, the efficiency is still at 3.57 micromole per joule. Osram OS uses a highly robust chip and can show a Q90 of 102,000 hours, offering the lowest system costs when incorporating a dual peak solution. First, simulations for your Horti system can be realized using the Horticulture tool from Osram OS, which is freely available online. Additionally, our application engineering team is glad to support you with all your technical questions. The best growing results require the best lighting technology. Osram Opto Semiconductors has a long-term product strategy to deliver the best performance in terms of efficiency, robustness, lifetime, and cost. Start your horticulture journey with Osram Opto Semiconductors.